Welcome back everyone. Today we are going to step back for a moment from the purely quantum world and look at a concept that is fundamental to both classical and quantum mechanics. It's angular momentum. Why start here? Well, our entire modern understanding of the atom was born from trying to explain observations that didn't fit with classical physics. So think back to the early 20th centuries. Niels Bohr was trying to explain the distinct sharp lines in the atomic spectrum of the hydrogen atoms. So H atom line spectrum. So at the same time, experiments by Rutherford, Geiger, and Marsden had just given us this new picture of the atom. So a tiny, dense nucleus with positive charge, with electrons having negative charge orbiting it. Something like this. So almost like a miniature solar system. So this planetary model, was a brilliant start, but it was incomplete. To truly understand why electrons behave the way they do, why they occupy specific energy levels, and don't just spiral into the nucleus, we first need a solid grasp of the physics of rotation. So that's where the angular momentum comes in. So let's discuss the circular motion. So let's start with something familiar, like linear motion. If an object with mass m, like this, is moving at a velocity v, it has a linear momentum p, which is simply mass times velocity. So it's a measure of the object's motion in a straight line. But what happens when an object moves in a circle? So there is an object with mass m, but now they are moving on the circle like this. So it still has mass and it still has velocity, but its motion is now rotational, right? Rotational motion. So for this, we need a new set of description. We can describe the rotation by its frequency, nu rod. So this is not actually v, it is Greek letter nu. So usually nu is used for denoting frequency. So it is rotation frequency. So how many circles the matter makes in a second? So the unit is cycles per second. From this, we can define the angular velocity. Which is omega rho. So this is simply 2 pi multiplied by nu rho. So So this tells us how fast the object is rotating in radians per second. So the unit is radians per second. So the linear velocity of this particle is related to angular velocity using v equal 2 pi multiplied by the radius of the circular motion, 2 pi r multiplied by nu rot. So simply 2 pi multiplied by nu rot is omega rot. So it is like r omega rot. So now, just as mass represents an object's inertia, its resistance to being moved in a straight line, so we have a rotational equivalent called moment of inertia. Moment of inertia. So which is denoted by capital letter I. So this describes how difficult it is to change an object's rotational motion. So for a simple point mass rotating around the center, it is calculated as, for a simple point mass rotating around a center, just as in this figure. In this case, the moment of inertia I is given as the mass multiplied by the r square. So with these pieces, we can define the rotational equivalent of a linear momentum, so which is the main focus of this subsection, angular momentum, which is denoted by small letter L, usually italicized small letter L. So the fundamental definition of the angular momentum is moment of inertia I multiplied by the angular velocity omega. So by substituting our previous definition, we can see that this is also equal to the more familiar form. The moment of inertia for this case is given as mr square, and the angular velocity is given as the linear velocity divided by the radius. So it is given as mvr. So in a sense, it is the amount of rotational motion that certain object possesses. So this parallel is incredibly powerful. So the kinetic energy K, or T in your textbook. For linear motion, we know that the kinetic energy T is given as the half of the mv square. So if we express this using momentum, we will get p square over 2m. So now look at the beautiful symmetry here. For rotational motion, the kinetic energy is half of the I omega square. And when expressed using angular momentum, this becomes 2I over angular momentum square. So this form are exactly identical. And you can see from the correspondence between the linear motion and circular motion, every concept has a direct counterpart. So mass corresponds to the moment of inertia, and the linear velocity v corresponds to the angular velocity omega, and linear momentum p corresponds to the angular momentum L. So the formula for the kinetic energy follow the same pattern. So let's summarize this subsection. So understanding these classical ideas is the essential first step. It gives us the language and the mathematical framework we need before we can make the leap to the quantum world, where we will discover that for an electron in an atom, angular momentum is not continuous, but quantized into discrete specific values. So not so surprisingly, nearly every property are quantized. And it is this quantization that ultimately explains the structure of the atom. And we will move to the next page. Okay, section 1.8, the title is Bohr assumed that the angular momentum of the electron in a hydrogen atom is quantized. So the keyword is angular momentum is quantized. So now that we have a grasp of angular momentum, so let's apply it to understand Niels Bohr's model of the hydrogen atom. Bohr's hydrogen atom model. In this model, we picture an electron revolving around the nucleus. There is a nucleus here, and the electron is revolving around the nucleus in a certain orbit. So this orbit is maintained by a balance of two forces. So there is a coulombic attraction between positively charged nucleus and negatively charged electron. So F inward is a coulombic force, and this is given as like this. So E is the elementary charge, and R is the distance between two objects, and epsilon 0 is the permittivity of the free space vacuum. And absolutely there is a force exerting outward like this way, because this is rotating object. So this outward force is given as a mass of the electron multiplied by the velocity square over radius r. So however, the classical physics presented a critical flaw in this model. So according to classical theory, an accelerating electron, because this electron is moving around the nucleus, which makes the circular motion, even though the speed of these electrons are constant, the direction of the moving electron is continuously changed, which means the forces are constantly applied for this object, electron. So this accelerated electron should continuously radiate its energy, which means causing it to lose speed and spiral into the nucleus. So in classical physics, it should behave like this. Then the electrons and the nucleus collapse to each other and there will be no atom in the universe. So in classical physics, the stable atom was forbidden object. So let's follow the Bohr's assumption. So absolutely Bohr already knew this problem. So to resolve this paradox, Bohr introduced two revolutionary assumptions. First, he proposed the existence of stable and stationary orbit where the electron does not radiate its energy. So second, and most importantly, he postulated that the angular momentum of the electron, angular momentum L, in these orbits must be quantized. So he stated that the angular momentum could only exist in integer multiples of a fundamental constant. So writing this rule as like L should be MEVR. We already derived this expression, and he thinks that this should be some multiples of fundamental constant and h bar. So this is a magical fundamental constant, and n should be 1, 2, 3 ... positive integer number, and h bar, this is the reduced Planck's constant. So these revolutionary assumptions have profound consequences. So we are taking a look at the allowed orbit and allowed energy levels. So with this revolutionary assumption, which means that the only orbits of a specific allowed radii are possible, and the radii are determined by the integer n. So let's take a look at this mathematically. The velocity of rotating moving electron, v, can be obtained from this equation. So v is given as the nh bar over MER, and we also have the one more equation from the force balance between the inward and outward force. So if E square over 4 phi square, this should be equal to so from these two equations we can derive that the expression for the radii r, and this is given as the very complex equation. So you can combine these two equations to derive the expression for r. And You will might notice that these are simply constant, even though it looks very complex. So this might be expressed as something like some constant a multiplied by n squared, and n should be positive integer. And we can calculate this a, and a is 5.29 multiplied by 10 to minus 11 meter. So we can visualize the allowed orbit. So the smallest possible orbit when n equal to 1 defines a fundamental physical constant known as the Bohr radius a0. So this value is simply a multiplied by 1 square, so it should be equal to a. So this is 0.529 angstrom. And you can go a higher level to find a larger allowed orbit. So people think that the smallest allowed radii, this should reflect the size of hydrogen atom in any way. And we will discuss and we will meet this number again when we are dealing with the wave function of the hydrogen atom. And magically, this number coincides to the position where we find the this distance corresponds to the point where the electrons are mostly reside. So the highest probability is achieved at this point. Okay, so we confirm that there is allowed orbits, and the radii of the allowed orbits are given as like this. Now let's look at the energy levels. So since the electron's total energy depends on its orbit's radius, so the energy is simply the function of the radius. So its energy also must be quantized. Energy also must be quantized. Why? Let's look at the mathematical expression. So energy consists of two components, the kinetic energy T plus potential energy V. So in this case, the potential energy V is simply the Coulomb potential energy, so minus 4 E squared. So if we plug into this into the total energy expression, and we know that the kinetic energy expression, so it is something like this. And you might notice that we can rewrite this part with the potential energy. So this will be left as a homework for you. So you can go up to the lecture note and find out the expression that can relate this with the radii r. Then you will result in the expression like this. And in the previous discussion, we expressed the radii with some constant multiplied by some quantum number. So let's plug this expression into here. That will give you some expression like so again, it looks very complicated, but this is some number, very complex number, but still anyway this is number multiplied by 1 over n square. So you will notice that n should be some positive integer. That means the energy level is also quantized. Okay. Now let's look at the transition between the allowed energy level. So far we discussed the hydrogen atom's structure, but still it is not directly correlated with the experimental observables, the line spectrum. Of course, this is a strong evidence why we have a discrete line spectrum rather than continuous spectrum, but still we cannot predict we still don't know the position of the peak. So let's discuss that. For frequency condition, the lowest energy level that is allowed n equal 1 is the ground state, and all higher energy levels like n equal 2, n equal 3 are called excited states. These excited states are unstable, and an electron will quickly relax to a lower state. Just think about the water you pouring from the top. So the water should go down to the bottom or the floor. So this is the key to explaining the hydrogen atom's emission spectrum. So when an electron jumps from a higher unstable energy to a lower, more stable one, this should emit the energy difference as a photon of light. So if there is energy level like n equal 1, n equal 2, n equal 3, 4, something like that. So if the electrons jumps from the higher to the lower energy level, something like this, then the energy difference, there should be some excess energy. This excessive energy will be emitted as a photon of light. So this is governed by the Bohr frequency condition. So we already have the expression for the energy here, and the energy difference delta E, the transition from the N2 to N1, then this should be something like this. And we know that this is also quantized energy level, this is also quantized energy level. That means the quantized number minus another quantized number, that should be another quantized energy, quantized number. So this the photon energy of emitted light, this is also quantized. So this means the h is simple constant, then only thing that can be quantized is the frequency of the emit light. So this is exactly why we see distinct lines in the spectrum. So this brilliant model perfectly reproduced the known Rydberg formula, which validating the Bohr's radical quantum hypothesis. So this the Bohr's idea was quite radical, and it is not based on any physical model, but still it can reproduce the very mysterious magical number observed in hydrogen atomic spectrum. So people think about, and now they are willing to accept the idea of the energy level quantization. So before we discuss further, let's take a look at how Bohr's model can be improved. So 1.9, the title is electron mass should be replaced by a reduced mass in the Bohr theory. So previously we discussed the Bohr model of the hydrogen atom. In there, key assumption we made was that the proton is much more massive than the electron, that we can consider it a fixed center with the electron revolving around it. So like this, the nucleus here, the electrons revolving around the nucleus. In this case, we consider that the position of the nucleus is fixed, but yeah, this simplifies the calculation significantly. However, in reality, things are more complex than we think, because we are not dealing with a one-body problem, but a two-body problem. So electrons are not the only free body in this problem. So nucleus is also a free body. So their interaction should make both objects move in the space. That means electron does not orbit a stationary proton. Instead, both the proton and electron revolve around their common center of the mass. So this should be more like, so there is a particle with mass m1, and there is a particle with mass m2. So there should be somewhere a center of the mass, and the distance between two particles is r. So rather than one fixed center and one moving around particle, actually both of them move around with respect to this center of mass point. So this is actually a two-body problem. So while this seems like a much harder problem to solve compared to a single body problem, there is an elegant mathematical technique that allows us to simplify it, like convert two-body problem into a one-body problem. This can be achieved by introducing a concept called reduced mass. Reduced mass, denoted by Greek letter mu. And the Greek letter mu, which represents the reduced mass, can be obtained from the mass of two particles. So 1 over mu should be the sum of 1 over m1 plus 1 over m2, which means the reduced mass m mu should be m1 m2 multiplication divided by m1 plus m2. So you can derive this expression. So we are going to take a look at very briefly. So center of mass can be defined like this. So with respect to the center of mass, we can define the two different distance. The distance between the particle 1 and the center of mass is r1. Similarly, we can define r2. So the definition of the center of mass will give you the one equality. So m1 multiplied by r1 should be equal to m2 multiplied by r2. So their value should be equal. And for sure, the sum of the two distance should be equal to the total distance r. So this is one of the exercise problem in the textbook. So you can combine these two equations, and now you can express each distance ri. So I should be 1 or 2 in this problem. This can be expressed using the mass and the total distance. So and similarly, R2 should be m1 multiplied by r divided by the total mass of the system, which should be m1 plus m2. So with this in your hands, we can calculate the moment of inertia. So we have two circularly revolving particles. So we are going to add up each particle's moment of inertia, m1 r1 square plus second particle's moment of inertia, m2 r2 square. So even though this expression looks quite complicated, but we can convert the ri, r1 and r2. We can convert this value using r, which makes expression much more simplified. So this will lead you to something like this expression. So if we replaced this part with like the imaginary particle, and the mass of that imaginary particle, like if we denote that mass as a mu, then we have now equation like moment of inertia of the two body system is now looks like a one body, the moment of inertia for a one body system. But now the mass is changed, right? So m1 and m2 are combined to give a single body with mass mu. Okay, so let's apply this process to our hydrogen atom. So for the proton-electron system, the two-body system, the reduced mass should be defined as mu should be proton mass multiplied by electron mass divided by the sum of the proton mass and electrons mass. When we plug in the values for the mass of the proton and electrons, we will find that the reduced mass is approximately 0.9995 mass of the electron. So it is quite trivial, right? Because the mass of the proton is much more massive compared to the electron's mass. So actually we can ignore this part, and we can expect that the proton's mass will be cancelled out, so we can expect that the reduced mass for a hydrogen system will be very, very similar to the electron's mass as expected. But still, this is not exactly the electron's mass. So even though it is a very, very small correction, but it still has some meaningful impact. So by replacing the electron's mass with a reduced mass, we can increase the accuracy of the Bohr model, and finally we can obtain much more accurate Rydberg constant. So at this point I would like to give you one more homework. So you can please calculate the Rydberg constant for the hydrogen atom, and please check that how theoretically derived Rydberg constant similar to the experimentally determined. So you will figure out that, wow, this is quite impressive. The number is quite close. This is one of the greatest scientific achievement in the scientific community. So there are many theories to explain the experimental observation, but there are not many cases where the such like Bohr theory achieves. Like this is really, really accurate prediction. So this refinement demonstrates a crucial point in physics. So even small correction to our models can lead to a significant increase in their predictive accuracy. Okay, this is for section 1.9. Let's move on to the next page. Okay, section 1.10, the title is Louis de Broglie postulated that matter has wave-like property. So far, our journey into quantum world has forced us to reconsider fundamental ideas about the atom, energy, and the momentum. So in this subsection, we are going to explore one of the most profound and counterintuitive concepts in all of modern physics. So wave-particle duality. So for centuries, light was understood to behave as a wave. Light, everybody think that, oh, light is a wave. It exhibits properties like diffraction and interference that are hallmarks of wave-like behavior. So diffraction, interference. I guess you already learned the diffraction and the interference, so I will not discuss these two concepts here. However, phenomena like the photoelectric effect. Let's go back to the Einstein's photoelectric effect. In that experiment, the observation of the threshold frequency and the linear dependence of the ejected electron's kinetic energy with respect to the incident light, those things cannot be explained by the wave character of the light. So those experiments, including the Bohr's atomic model itself, that light also behaves as if it's made of discrete particles. Photoelectric effect. And Bohr's atomic model. So, light, which we thought of as a wave, now it has particle properties in some situation. So, in our macroscopic world, we feel more comfortable. The matters are matter, particles are particle, the waves are wave. That is our thought in the macroscopic world. So if someone says like, oh, your cell phone behaves like wave, then you might think like this guy is a little bit awkward. That doesn't make sense. But in a microscopic world, for like an atom, the light, then those very, very small, tiny system can have both the characteristics of the particle and the wave. So this led the French physicist Louis de Broglie to ask a revolutionary question in 1924. If waves can act like particles, then can particles act like waves? Doesn't matter, like electrons, protons, atoms, and even everyday objects, do they have a wave characters associated with it? So de Broglie proposed that the answer is yes. So during his PhD course, he is not an experimental physicist, so he just postulated. So postulate means the assume with thoughtful evidence. So still there is no experimental evidence. So he postulated that any particle with momentum p also has a corresponding wavelength, which now we call the de Broglie wavelengths. Lambda. So the relationship he proposed is beautifully simple. So the matter wavelengths lambda, this will be equal to the Planck constant h divided by the particle's momentum p. So how this beautiful equation where does this beautiful equation come from? So actually this is from the Planck's relation. Energy is given as a HANU, and Einstein's mass energy equivalence. Energy is mass multiplied by the square of the speed, light speed. And these two properties should be same. That means HANU should equal to mc square. And the frequency nu, this is simply given as the speed of light divided by the wavelengths lambda. So if we cancel the common factor c on the both sides, that will give you equation something like this. And we can consider this as the photon's momentum. So now we have a de Broglie wavelengths. So these implications are quite staggering. It suggests that the electron, which we have been treating as a tiny particle orbiting the nucleus also behaves like a wave. So this concept was experimentally confirmed a few years later, showing that the beams of electrons could be diffracted just like light waves. So the wave-particle duality is not just a theoretical curiosity, it is a fundamental property of our universe. And it is the cornerstone upon which the entire quantum mechanics is built. So we can move on to the next page. So how de Broglie formula is used to strengthen the Bohr's atomic model. Section 1.11, the title is The de Broglie formula gives an alternative rationalization of Bohr's first postulate. So in the previous section, we introduced Louis de Broglie radical idea that particles like electrons have a wave-like nature. So wave-particle duality. So this concept does more than just add another strange rule to the quantum world. But actually, this provides a beautiful and physical explanation for one of the Niels Bohr's radical key assumptions. So let's go back to Bohr's atomic model and recall the Bohr's first postulate. So Bohr postulates that the angular momentum of an electron in an hydrogen atom is quantized. So angular momentum L and VR should be some multiples of reduced Planck constant. So N should be 1, 2, 3. So Bohr introduced this as a necessary rule to make his model fit the experimental data. But he didn't have a fundamental reason for why it had to be true. So that's why we call this is assumption. So actually, de Broglie's work provides the reason for the quantization of the angular momentum. So briefly, and let's stop thinking of the electron as just as a particle, and instead picture it as a wave traveling in a circular Bohr's orbit. So if there is a Bohr orbit like this, and no more particle, rather than particle we think like wave, such like this. So for an orbit to be stable, the electron's wave must not interfere with itself and cancel out. So for example, like which means the starting position of the wave somewhere here and the end position of the wave should match to be a stable wave on the circular motion. So what happens if there is a mismatch between the starting and the end point? That means the electron's wave interfere itself, and finally it diverges or it decays out, so which physically doesn't make sense. So for a stable circular wave, we can hypothesize and we can argue that the electron's wave should form a standing wave. So What does this mean? It means that after completing one full revolution around the circle, the wave must connect with its starting point perfectly in phase. So if you carefully look at and carefully draw some several possible case for the stable standing wave on the circular ring, you will notice that the circumference of the orbit, 2 pi r, should be an exact integer multiple of the electron's wavelengths. So this is a necessary condition for the formation of a standing wave. This should be equal, and absolutely n should be positive integer. So if the circumference is not an integer multiple, the wave will be out of phase and leading to destructive interference that could cause the wave and the electron's orbit to vanish. So this is the quantum condition for a stable orbit. And now we can simply substitute de Broglie's relation into this condition. So instead of lambda, we are going to put the de Broglie's matter wave. That means 2 pi r should equal to mv over nh over mv. And we rearrange this equation by multiplying both sides by mv and dividing by 2 pi. Then we will obtain mbr equal nh bar. So you might realize that this is the exactly same as the Bohr's first postulate. What Bohr had to assume without proof, de Broglie was able to derive from the fundamental principle of the wave-particle duality. So the quantization of the angular momentum, actually it is the natural consequence of electron behaving as a stable standing wave in its orbit. So now we can rationalize the Bohr's first postulate. Now let's move on to the next page. Section 1.12 is about the de Broglie's wave are observed experimentally. So Louis de Broglie hypothesis that matter possesses wave-like properties was one of the most profound and revolutionary ideas in the 20th century's physics. But this hypothesis, no matter how elegant and well explaining the experiment, is only as good as the experimental evidence that supports it. So in this subsection, we will discuss the key observation that transformed the de Broglie's idea from a theoretical concept into established scientific principles. So the first is X-ray diffraction. One of the definitive characteristics of wave is their ability to diffract. So diffraction occurs when a wave encounters an obstacle or aperture, causing it to bend and spread out. So classic way to observe this is by passing waves through a regularly spaced grating, which produces a characteristic interference pattern. So if we have some regularly spaced grating like this, And when you shine the light from this direction, so it propagates like this. So, and we are going to detect the light at the another side. So what happens if the particles is only particle behaves only like what happens if the light behaves only like a particle? Then we will see the depending on the direction of the light, we will observe the some shape like this. So there is a very bright region, and it's getting darker and darker as we away from the peak position. But the actual observation is like, rather than this peak position, we observe some bright side, dark side, bright side, dark side, like alternative pattern, something like please understand my bad picture. So it is totally different from the particle's nature. So the reason why we observe this bright region and dark region is the result of constructive and destructive interference pattern. So scientists had long used this technique with X-rays. So which are a form of electromagnetic radiation by passing them through a crystalline solid. The regular repeating arrangement of atoms in the crystal acts as a natural diffraction grating. So the result is a distinct pattern of bright spots as seen in X-ray diffraction. So we can determine the 3D structure of the crystalline solid. So the crucial test for the de Broglie hypothesis was to see if a beam of particles would produce the same kind of pattern, right? So de Broglie's argument is that particle also has the nature of wave. Then, if we let the particles pass through these regularly spaced gratings, then we should observe the same pattern that was made by wave. So in 1927, the Davison and Germer conducted a landmark experiment where they fired a beam of electrons at a nickel crystal. So the result was astonishing, as you expected. The electrons diffracted, creating a pattern that was strikingly similar to one produced by X-rays. So the beams of electrons and X-rays, they make nearly the same diffraction pattern. So we think that electrons are particle and X-rays are waves, but this particle can make the same pattern as the wave made. That means the particle also has the nature of the wave. So this demonstrated that electrons, which had always been considered particles, were indeed behaving like waves. The diffraction pattern from aluminum foil, for example, is nearly identical whether it is generated by X-rays or by electrons. You can see the beautiful picture in our textbook. So this discovery was not just a scientific curiosity, it also opened the door to powerful new technologies. So the most significant of these examples is the electron microscope. So the resolving power of any microscope is fundamentally limited by the wavelengths of the probe beam. So resolution is strongly correlated with the lambda of probe light. So we cannot determine the smaller structure, a structure which is smaller than the wavelengths of the probe light. So in an electron microscope, we use a beam of electrons instead of light. So according to de Broglie's equation, so lambda is h over p. The wavelength of electron is inversely proportional to its momentum, right? So we can easily control the momentum of an electron by accelerating it through an applied voltage. So by using high voltage, we can give the electrons a large momentum. So if you apply large potential, then the electrons will gain high velocity, and that results in high momentum, which in turn results in extremely small de Broglie wavelengths, which can be much smaller than the wavelengths of visible light. So this is the key advantage of the electron microscope. The smaller attainable wavelengths of the electrons offer a far more precise probe, allowing us to visualize the matter at the atomic and molecular scale, revealing the details that would be forever invisible to conventional light microscope. So the experimental confirmation of the de Broglie's waves not only solidified our understanding of quantum mechanics, but also provided us with an invaluable tool to explore the microscopic world. Okay, let's close this section at here and move on to the next page. Okay, so section 1.13, certain two-slit experiments exemplified wave-particle duality. So this is also very important section, but I will not discuss this subsection in our lecture because most of the contents are already discussed in general physics lecture. So let's move on to the next section. Section 1.14, which is the last subsection in the chapter 1, is about the Heisenberg uncertainty principle. So the title is Heisenberg uncertainty principle states that the position and the momentum of a particle cannot be specified simultaneously with unlimited precision. So this is quite interesting principle, so let's take a look at this principle very closely. So our discovery of the wave-like nature of particles, such as electrons, forces us to abandon some of our most basic classical intuition. So if a particle is also a wave, particle also can be a wave, then it cannot have a precise, well-defined position and momentum at the same time. So this fundamental limitation was articulated by Werner Heisenberg in 1927 and is now known as the Heisenberg uncertainty principle. So this principle states that it is fundamentally impossible to simultaneously determine with perfect accuracy both the position and the momentum of a particle. So there is an inherent trade-off. If you want more precisely measure the one property, then you are going to have a less precisely measured value for the another quantity. So this is like if you want really highly accurate position, then you will get less accurate momentum value, and vice versa. So if you want really highly accurate momentum value, then you will obtain the less accurate position. So I wanna emphasize that this isn't a statement about the limitation of our experimental equipment. So this is not our limit of current experimental equipment. So it is a fundamental property of the universe itself, stemming directly from wave-particle duality. So even though we have a much more improved equipment, still we have some trade-off between the position and the momentum measurement. So let's try to let's try to understand this deeper. So imagine a particle's wave. If the wave has a single well-defined wavelength, then its momentum is known with great precision, right? So wave particle also has a nature of the wave. Then if this wave is this wave can be characterized by single wave and well-defined wavelengths, then we will have a very accurate momentum value, since the momentum simply is given as the Planck constant divided by its wavelengths. This is just from the matter wavelengths de Broglie equation, right? However, a wave with a single wavelength is a continuous sine wave extending infinitely through space, right? So the wave extends infinitely. So that means its position is completely uncertain. So it's everywhere at once, right? The wave is nearly infinite. So this is the example of highly accurate momentum, but so this is like very precise value. So in this case we are going to have no information for the position x, right? Now we want to locate the particle, which means we want to have a really accurate position. That means we need to create a wave packet. So a wave that is confined to a small region of space. So you might see the wave packets in physical chemistry class. So if we have a parabolic potential curve, then the wave packets looks like this, and these wave packets move back and forth within the parabolic potential. So we do this by adding together many different sine waves with different wavelengths, right? So we are going to add the sine wavelengths with this with wavelengths lambda 1, and another sine wave with wavelengths lambda 2, and maybe another sine wave with wavelengths lambda 3. So there, if we add multiple sine waves, then we can make this well localized wave. So the more waves we add, the more localized the wave packet becomes, and the more certain we are of the particle's position. That means as the number of waves increases, the more accurate position information, which means the error in measuring the position will be smaller and smaller. However, because we used many different wavelengths, we have introduced a large uncertainty in the momentum, right? Each wavelength has its corresponding momentum P1, P2, and P3. Like all of them contribute the total angular momentum. Total momentum. So in this case, delta P becomes much large. So this intrinsic trade-off is captured mathematically in Heisenberg's very famous inequality. So the error in measuring the position and the error in measuring the momentum, if we multiply these two values, then this value is bounded by the Planck constant. So if you want really high accurate value, that means accurate value of the position, that means the error in measuring the position will be getting close to 0. But this value, the multiple of these two quantity, should be larger than h. So P goes to infinity, diverge. So we don't have any information regarding the momentum. So this principle fundamentally destroys the classical idea of a particle following a well-defined trajectory, where we know its exact position and velocity at every instant, right? So in our classical world, so some case like this, if I drove the car and there is a speed limit like 100 kilometer per hour, then I pass through this like at the 110 kilometer per hour. Then the police will notice that I drive my car too fast, and they will send a ticket to my home. So the police can determine the exact position of my car, right? So I drive the car at here, so they know my position. In addition, they also exactly measured my velocity, which is associated with the momentum. So in our classical world, we think that it is possible to measure the position and velocity at unlimited precision, but this is not totally true in the microscopic world. Then you might think that, oh, there might be two different principles that govern the microscopic world and the macroscopic world, but this is not the true. So this rule, this principle is actually universally common principle. So this applies to every details of our life. But our daily life consists of very big stuff compared to the atomic scale. So even there is some error in this value and some error in the delta p. So this value still can be the multiplication of these two quantities still can be larger than h, even though we could not notice their difference, right? Something like, so I might drive my car like 100.105 kilometer per hour. So there is some like measurement error, right? But still the difference like this. This is still huge value, so we can still have very small error in the measuring the position. So remember that this value is really large value. Some scale like 6.6 multiplied by 10 to minus 34 joules sec. So in our everyday life, so we don't really realize the Heisenberg uncertainty principle. This is the last section in the chapter 1, and we are going to meet at the chapter 2 again. Thank you for your attention.